Welcome dear learners, this is Aishwarya, Assistant Professor, Department of Chemistry, St. Joseph's College of Arts and Science for Women, Hosur. In this video, we are going to discuss about the theory of the coordination complex. First, we are going to see about the Werner theory. In 1893, Werner proposed a theory which commonly known as the Werner coordination theory. He isolated different complex compounds from the reaction of cobalt, chloride and ammonia and called the cobaltamine. He proposed the Werner coordination theory to explain the nature of the bonding in coordination complexes. It suggested that metal ions have the primary and secondary valencies. Primary valency equal to the metal oxidation number. Secondary valency is the number of atoms directly bonded to the metal, that is the coordination number. Werner theory. Metal possess the two types of valencies. First one is the primary valency and secondary valency. Primary valency are called principal ionizable valency. In metal, exhibit the formation of its simple slots. These are the primary valency refers to the oxidation state. Primary valency is the ionizable. Secondary valency, when metal atom or cation expands towards neutral molecules or negative group in the formation of its complex ion. Every metal cation has the fixed number of secondary valencies. So secondary valence is the number of atoms directly bonded to the metal. Coordination number places those molecules and ions within the sphere in brackets. Free anion that dissociate form the complex ion outside the bracket. Many coordination compounds have the having same metal and same ligands. So secondary valency is called also the coordination number of the metal cation. Every metal atom has a tendency to satisfy both the primary and secondary valency. So primary valency are satisfied by the negative ion. Secondary valency are satisfied by the negative ions or neutral molecule, that means ligands. So negative ion may satisfy both types of valencies. While writing a structure of a given coordination compound, the primary valency are generally indicated by the broken line. Secondary valency are shown by the solid line. The secondary valencies are always directed to the fixed position in the space and leads to the definite geometry of the coordination compounds. If metal ion has the 6 secondary valencies, so that is arranged in the octahedral. If a metal ion has the 4 secondary valency, it is a tetrahedral or square planar arrangement. The secondary valencies determine the stereochemistry of the complex, but the primary valency is a non-directional. The many coordination compounds are the same metal, same ligand. So in compound 1, the chlorine is not in coordination sphere. Three chlorine ions gives the orange color. In compound 2, three chlorine ions in the outside the bracket, so it gives the purple color. In compound 3, one free chlorine ions, it gives the green color. So in compound 4, there is no free chlorine ions in the outside the bracket. The central metal and the ligand directly bonded to make up to the coordination sphere of the complex. In cobalt trichloride, in all 6 ligands are NH3 and the 3 chlorine ions are outside of the coordination sphere. In this compound, the 5 NH3 groups and 1 chlorine atom bonded to cobalt and the other 2 chlorine atoms are outside the sphere. Werner proposed putting all the molecules and ions within the sphere and in brackets, and those free ions that dissociate from the complex ion when dissolved in water outside the bracket. This approach correctly predicts there would be two forms of COCl3. two forms as two chlorine next to each other, the other as the chlorine opposite to each other. The one in the first one, the cis chlorine atoms gives a violet color, and the other one is it gives the opposite side, it gives a green color. So next one is we are going to see about the Sedgwick theory. Sedgwick theory explains the formation of the coordination compound. Sedgwick electronic theory states that the ligand donate the electron pair to the central metal atom, thus form the number of their coordinate bonds. It donates one electron each other for each carbonyl. Here ligands are donors, and the central metal ion is acceptor. So total of three electrons are contributed. Sedgwick electronic theory explains the formation of coordination bond. According to theory, coordinate bonds are formed when the ligands donate the electron pair to the central metal atom. Next one is the effective atomic number, that is the EAN rule. The sum of the electrons on the central atom, Lewis acid, including those donated from the ligand, Lewis base, should be equal to the number of electrons on a noble gas element found in the same period which metal is situated. That effective atomic number theory was first theory explained the concept behind the complex compound formation. This theory given by the Sedgwick. Therefore, the theory is known as the Sedgwick rule. In a complex species, the sum of electrons present in the central metal atom or ion, those donated by the ligands, is called the EAN of the central metal atom. Let us take the case. The oxidation state of the cobalt in the complex ion is +3. Number of electrons in the cobalt is 27. So number of electrons in the cobalt of the complex 27 minus 3 is equal to 24. Number of electrons donated by the 6NH3 ammonia ligands. So 6 into 2 is equal to 12. So effective atomic number is 36. It related to the is equal to the noble gas krypton atomic number. So it is follows the EAN rule. The EAN of the central metal atom given complexes species is given by the central metal atom is equal to atomic number of the metal atom minus oxidation number of the metal atom plus number of electron donated by the ligands. So next one is drawbacks. The donation of electron pairs to the central metal ion produce an improper accumulation of negative charge on this ion. Such condition is not fair. Some complexes, nickel, cobalt, are not follow the EAN rule, even they are stable. Metal are electropositive in nature. How they may many accept electron from ligand not explained. The next one is the limitation of Werner theory. So the Werner theory was not able to explain a number of properties of a coordination compound. So this why only certain elements form coordination compound and not others. Why the coordination sphere has the definite geometry, and why these compounds possess a definite magnetic and optical property. So these are the things not explained by the Werner theory. So these are the limitations for the Werner theory. Thank you.